Hey guys, in this video we're talking about Le Chatelier's principle. So this is Le Chatelier's principle, and it says that when a system that's at equilibrium is disturbed, and we'll talk about what that means, disturbed, the position of the equilibrium will shift so as to return to equilibrium. And so this is what it means. If you were disturbing the system by the equilibrium by adding a reactant or product or removing a reactant or product at this point. There's other ways to do it, which we'll talk about. So Le Chatelier's principle says that if a reactant is added or a product is removed, the system will shift to the right. We saw this before. This just says that Q is less than K. Because remember, if we add a reactant, the denominator in Q becomes too big, which means the value of Q is too small. And in order for it to get back to be equal K, we have to make more products. Same thing if we remove a product. If we take a product away, the numerator now in Q is smaller than that in K, and so the equilibrium will shift to the right to make more products so as to get Q equal to K and go back to equilibrium. On the other hand, just the opposite. If we remove a reactant or add a product, the equilibrium is going to shift to the left because when we do either of these, Q is greater than K, and we know when Q is greater than K, the equilibrium shifts to the left, back to the reactant side in order to achieve equilibrium. So that's basically Le Chatelier's principle. So let's apply it. So the question is, how will this system that's at equilibrium shift when we do each of the following, A, B, C, D, and E? And so why don't you guys go ahead and figure it out. The choices are shift to the right, shift to the left, or no change. And when you figure it all out, come on back. Welcome back, guys. So first of all, if sulfur dioxide is removed, we're removing some sulfur dioxide. Now we get a value of Q less than K. Equilibrium will shift to the right. So shifts to the right. Next, oxygen is added. So we're adding a product, it's going to shift to the left. Just like that. Sulfur trioxide is added. We're adding a reactant, it will shift to the right. Sulfur trioxide is removed, just the opposite. We're removing a reactant, so the equilibrium shifts to the left. Adding a catalyst. Remember, the only thing a catalyst does, guys, it lowers the activation barrier. It does not affect the equilibrium at all. So this one, no change. There we go. That's all there is to it. Now, other ways we can disturb the equilibrium. If we have gases involved, we can sometimes affect the equilibrium by changing the volume. It ends up. So the effective pressure changes. The way we can change a pressure is by adding or removing a reactant or product, because now we have more gas particles or less gas particles in the same container. So we're assuming here that the temperature stays the same and the volume stays the same, right? But if we add or remove something, then the same thing happens as before. Le Chatelier's principle. If we add a reactant, it shifts to the right. Add a product, it shifts to the left, and vice versa. Now, this is a good one to remember. If we add an inert gas, it has no effect whatsoever. So we can pump that thing full of, neon, and it's not going to change the equilibrium. Now, if we change the volume at constant pressure and temperature, then things start happening. If we increase the volume, the equilibrium will shift to the side that has more gaseous species. So we can't say left to right because it depends on the actual reaction, right? So what you do is you look at the balanced chemical equation and you add up the coefficients of only the gaseous reactants and products. Whichever side has, either one side will have more than the other, or they'll be the same. If they're the same number of gaseous reactants and products, then changing the volume at constant pressure and temperature does not affect the equilibrium. But if we increase the volume, we're going to shift to the side with more gaseous species. So it makes sense. If we increase the volume, there's more room, so we're going to allow more of the gases to exist. On the other hand, if we squeeze it, if we decrease the volume, the equilibrium is going to shift to the side that has fewer gaseous species. So for example, in this reaction right here, okay, if we reduce the volume, if you decrease the volume, then it's because there are 2 gaseous species on the right, 3 plus 1 is 4 on the left. There are more gaseous molecules on the left than on the right. So by decreasing the volume, reducing the volume, it's going to shift to the right in this particular case, the side that has fewer gaseous particles. And if there were fewer particles on the left, then it would shift to the left. If we increase the volume, this equilibrium will shift to the left because that's the side that has more gaseous species. 3 plus 1 is 4, which is greater than 2. This is a useful piece of information. If you're if you're a chemical engineer and you're working on large scales, you can sometimes drastically affect your yield just by reducing or increasing the volume. All right. So the other way we can disturb the equilibrium, guys, is by changing the temperature. Because remember, when we change the temperature, we change the value of the equilibrium constant, K. And the way to think about this in terms of Le Chatelier's principle is to think about the thermal energy as a reactant for an endothermic reaction and as a product for an exothermic reaction. And that makes sense if you think about it. In an endothermic reaction, energy has to be put into the system, so it's a reactant. In an exothermic reaction, thermal energy is released. It's a product. So for an endothermic reaction, the value of K increases with temperature. We get more products because in this case, we would think about the enthalpy, the energy, as a reactant. So we're adding more reactant, shifts to the right, we get more products. On the other hand, for an exothermic process, the value of K decreases with temperature. As we increase the temperature, the size of K gets smaller, which means we shift the equilibrium to the left. There are fewer products, more reactants. So for example, in the decomposition of dinitrogen tetroxide to make 2 molecules of nitrogen dioxide, it's an endothermic process. So we can think about it as let me do it this way, as the energy being can I do this? No. A reactant. And so if we add thermal energy, the equilibrium will shift to the right and we'll make more products, nitrogen dioxide. If we cool it down, if we lower the energy, the equilibrium will shift to the left and we'll have fewer products and more reactants. So that's the effect of temperature. So here we go. For this equilibrium, carbon monoxide reacting with hydrogen to make methane and water, there's delta H. We want to know what the effect of each of the following will have on the equilibrium. So why don't you guys figure this out real quick, and when you get answers, come on back. Welcome back, guys. So if we remove water vapor, that's this is a product, the equilibrium will shift to the right. Whoops. If we increase the temperature, so this is an exothermic process because delta H is negative, so the energy is a product, so by increasing the temperature, adding more energy, the equilibrium will shift to the left. If we add 1 atmosphere of argon gas in a rigid container, nothing happens because argon is an inert gas. No effect. If we remove carbon monoxide, that's a reactant, so we will shift to the left. And if we double the size of the container, so we're increasing the volume at constant temperature and pressure, well, we have 2 moles of gaseous products. 3 plus 1 is 4 moles of gaseous reactants. It will shift to the side, as we increase the volume at constant temperature, to the side with more gaseous species, so it'll shift in this case to the left. And that's all there is to it, guys.